Hi guys, so today we're going to be talking about balloon geometry, in particular domain and molecular geometry for our interactive concept number 7. Okay, so molecular geometry is a three-dimensional arrangement of atoms that make up a covalently bonded molecule. And remember, a covalently bonded molecule is one in which electrons are shared between atoms in order to achieve a stable electron configuration. The octet rule says that atoms want to have 8 electrons in their valence shells to achieve stability. The valence shell electron pair repulsion model, or VSEPR, predicts the shape of the molecules and ions by assuming that the valence shell electron pairs are arranged about each atom so that the electron pairs are kept as far away from one another as possible, minimizing electron pair repulsion. And the direction of and space of the bonding pairs is what gives you the molecular geometry. So let's talk about molecular geometry in balloons. So when using balloons to model VSEPR, it's important to know what each part of the balloon represents. So the balloon itself is going to represent the electrons of the atom. In a covalently bond, these electrons will be shared between the bonded atoms. The nucleus of the central atom is going to be signified by the knot of the balloon. So down in here, the big ends of the balloons, okay, is where another atom would be bonded with the central atom of the molecule. So we're going to have the central atom will be bonded here at the knot. Another atom would be on this side of the balloon, and all in here would be the electrons of the balloon that are being shared. Okay. So our first electron domain geometry is linear, and in a linear electron domain geometry, we have a total number of 2 electron domains. We have 2 bonded pairs and no lone pairs. It's an AB2 molecule with the electron configuration of 2sp. I chose carbon dioxide as my linear molecule. So in this case, my carbon would be my central atom, my oxygen would be on either side, and then the electron pairs that they're sharing would be here on the balloons. Okay, and the molecular geometry for this then would be linear because it looks like a straight line with a bond angle of 180 degrees. Okay. The next electron domain geometry is trigonal planar, and the total number of electron domains is 3 for this particular geometry. It has no lone pairs. It is an AB3 molecule, and it has electron configuration of 3sp2. I chose boron trichloride for mine, BeCl3, for the example. And you can see there are no lone pairs here. We get this kind of triangular shaped balloons here. Okay. There's no lone pairs, and has a bond angle of 120 degrees with trigonal planar as my molecular geometry. Also in my trigonal planar domain geometry, which also with 3 domains, 2 bonding pairs. But if we take one of these bonds away, and we only had 2 bonded pairs and 1 lone pair, so if this was not here, it's still an AB2 molecule. It would be a bent molecular geometry. There would be a lone pair, so right where this balloon would be a lone pair. You can see it here in my diagram, so the lone pairs are right there. It's still a 120 bond degree angle. So, also, next we have our electron domain geometry of tetrahedral. I did choose methane. It has 4 electron domains. It's got 4 bonded pairs. There are no lone pairs in a tetrahedral molecular geometry. There are 4 bonded pairs, no lone pairs. It's an AB4 molecule, electron configuration of 3sp2. And so that's what it looks like. You can see it looks almost like a little pyramid there. Okay. And like I said, for the tetrahedral molecular geometry, there are no lone pairs. And our bond angles are 109.5. And I chose methane, so CH4. Also in our tetrahedral domain geometry is trigonal pyramidal. So trigonal pyramidal has 4 domain electrons. It has 3 bonding pairs, 1 lone pair. So that means one of these guys would be gone. They're not gonna be bonded with another atom. It's an AB3 molecule, 4sp3. And you can see the placement of the lone pairs is with the nitrogen in this particular case. And again, our molecular shape is trigonal pyramidal with our 109.5 degree angle. Oh, and that was actually ammonia there. Yes, that was ammonia. Sorry, guys. In our electron domain geometry for tetrahedral, I chose water as my bent molecular geometry. And so their total number of electron dot domains is 4. We have 2 bonded pairs, and this time we have 2 lone pairs, so 2 pairs of electrons that are not bonded to another atom. It's still an AB2 molecule. We have a 4sp3 configuration. You can see that the lone pairs are on the oxygen molecule because oxygen is more electronegative than hydrogen, so it hogs the electrons. And our geometry is bent, and it's still the 109.5 bond angles there. Sometimes our hydrogen is a little closer. All right, our next electron domain geometry is trigonal bipyramidal, and I chose phosphorus pentachloride. And we have total number of electron dot domains is 5. We have 5 bonding pairs, so 5 atoms bonded. There are no lone pairs here, and our type of molecule is AB5. It has an electron configuration of 5sp3d, because we have that d orbital now, and you can see that. I can get this to cooperate with me and not fall apart. There it is. Okay. You can see I've got 1, 2, 3, 4, and my 5th one is right there. Okay. So electron dot domains there is 5. We have the number of bonding pairs is 5. Our lone pairs is 0 in this case, and it's an AB5 molecule with the electron configuration of 5sp3d. It still has that d orbital. This particular one, there is no lone pairs, and so this molecular geometry is trigonal bipyramidal. And again, I chose phosphorus pentachloride, and so we have a couple different bond angles here. So from this atom to this atom, it would be a 90-degree angle, but from this, the side atoms, okay, they would have 120-degree bond angles. Remember, the electrons are pushing each other as far away as possible. Also in our trigonal bipyramidal domain geometry is a shape called seesaw shaped. As for molecular geometry, it has a total number of electron domain is 5. Our bonding pairs is 4. We have 1 lone pair, so one of our electron pairs is not bonded to another atom. It's an AB4 molecule with a 5sp3d electron configuration. You can see the lone pairs there. They are connected to the sulfur atom, okay? We have 120 degrees of a bond angle here, and then our sulfur to our fluorine is going to be a 90 degrees. Again, also in the trigonal bipyramidal electron domain geometry, we have what's called a T-shaped molecular geometry. We have a total number of electron dot domains is 5. There's 5 electron atoms available. There are 3 bonding pairs, 2 lone pairs, so there's 2 spots where there's no atom bonded. It's an AB3 molecule with a 5sp3d electron configuration. Again, there's 2 lone pairs attached to our bromine, and it is T-shaped. The last one in trigonal bipyramidal is xenon difluorine or fluoride, and its total number of electron dot domain is 5. We have 2 bonded pairs, 3 lone pairs. It's an AB2 molecule, 5sp3d. Our lone pairs are again attached to the xenon, and since there are 3, it's like these 3 don't exist, it would be a linear shape. Okay, so a linear molecular geometry. Okay. All right, our last electron domain geometry is octahedral, and I chose sulfur hexafluoride for this one. Their total number of electron dot domains is 6. Their number of bonded pairs is 6. We have number of lone pairs is 1. Or sorry, number of lone pairs is 0. My balloons are falling apart. It's an AB6 molecule, 6sp3d, 2 electron configuration. Our lone pairs, there is none here. And our molecular geometry is octahedral. Okay. And sorry, the bond angles are 90 degrees. Our next one in our domain geometry of octahedral is we still have a dot domain of 6. We have 5 bonded pairs. Number of lone pairs is 1, and is an AB5 molecule electron configuration of 6sp3d2. And that molecular geometry is square pyramidal. And so here, I don't know if you can see this now, is my octahedral balloon configuration. And again, those bond angles are 90 degrees. The last one here is we have xenon tetrafluorine. or fluoride, sorry, with the total number of electron dot domains of 6. So it is an octahedral domain geometry. We have 4 bonded pairs, 2 lone pairs. It's an AB4 molecule, 6 sp3d2 electron configuration. Our lone pairs are located on the xenon atom, and this particular one is square planar. And again, it has electron angles of 90 degrees. Okay. All right, that was a lot in a mouthful. I hope you enjoyed that presentation. Thank you.